Hello and welcome back again. So in this video, we are going to build a connection between stochastic differential equation and the corresponding Fokker-Planck equation. So we know that we have an SDE and the solution of this SDE is the underlying process XT. So there is a process that satisfies this stochastic differential equation. And the solution of a Fokker-Planck equation is the law of that process XT. It means the probability of this XT at any time t. And obviously, this is an stochastic differential equation, while a Fokker-Planck equation is a partial differential equation. And the simple example is the SDE looks like this one. dxt is mu of xt dt plus sigma of xt dbt. And when we solve this one, we get the underlying process xt. And this is a PDE that we call a Fokker-Planck equation corresponding to this stochastic differential equation. And the solution of this Fokker-Planck equation is this P of xt, which is the law of this process xt, or what is the probability of xt at any time t. What is the probability of xt taking a value, certain value at time t? So this is the overall game. So our idea is to take this SDE and convert into this Fokker-Planck equation. And the idea is very simple. We'll only apply what we call Ito's formula. And Ito's formula is if we see it from a computational point of view, from a applied mathematician point of view, it's simply Taylor series and nothing else. And you truncate your Taylor series to certain terms. That's it. Okay. So let's take the SDE, which is dxt is mu of xt t dt plus sigma of xt t dbt. Okay, first of all, to drive this Fokker-Planck equation, I'm taking a general function of this process xt. So this is like, let I have a function of this one, where this function satisfies some usual properties, like this function is C2. It means you can differentiate this function twice with respect to x, and there's no any problem in that. This is the overall game. Now what am I doing? I'm applying Ito's formula on this function. Ito's formula is simply Taylor series, as I told you. Like the differential of f is differentiate f partially with respect to x. So the subscript notation is like, this one is differentiate partially with respect to x. And then I will write dxt. Like once you differentiate, you write dxt. This is how Taylor series works. Plus 1/2 second derivative. It means fxx. It's a second derivative with respect to x. And dxt square. Okay, now I will put the value of dxt, which is I'll put the value of dxt here and dxt here. And this is the value of dxt that I have. This is the next thing that I'll do. So it will give me fx, and dxt is mu of xt t dt plus sigma of xt t dbt plus 1/2 xx dxt square. It means I'll write dxt and I'll simply square it. So what am I doing? I'm just copying this one. So, oh, sorry. So I need to paste it here back, and I need to paste it here as well. Okay, it creates certain problems. So what am I doing? I'm taking this a little bit here, and then taking this here, and then I'm going to square it. So you saw that this is dxt, which is the value of this one, and this is dxt. Again, the same value and square. Good to go. Now, there is a simple rule that I'll apply here. Since I'm doing everything from a computational point of view, so I would not give the reasoning behind many terms here. One thing is dt when squared is 0, and when dbt is squared, the answer is equal to dt. So this is defined like this. So when I write triangle, this is defined like this. And dt times dbt again is 0. So this is my Ito's table that I will apply here. So these are the general rules that I'm applying, and I'm not giving any reasoning why this happens, but we can prove this thing. So then I get like df is equal to, so I'm just expanding this first term with this one and this one, and maybe I will write in compact form without writing all the indices, all the values inside the bracket, maybe. So this one is like mu fx dt. You can see here, this is mu. I'm not writing what is inside. It is understood that mu is function of x and t and fx and dt. And then I'll write sigma fx dbt. So plus sigma fx dbt plus, so I will apply Ito's table here. You know very well, this is one term plus two terms. I call this A and this B, and I'm squaring these. So the answer will be A square plus 2AB plus B square. It means square the first term. The first term contains dt, so if I square it, I'll get 0 by this law. So if I multiply these two terms, that would be 2AB, so that would be dt. So if I multiply these two terms, that will be dt times dbt, this is again 0. So I will only incorporate the last term, which is b square. B square means the square of this one, which is sigma square dbt, and dbt square is defined to be dt. So this is the law from Ito's table. So I have 1/2 fxx sigma square dt. Now you can see here, I have a term corresponding to dt. I have a term corresponding to dt. I will like keep these terms of dt together and keep the dbt term separate. So it will give me df is equal to, so what do I have? Mu fx plus 1/2 sigma square. And what do I have? Fxx. Okay. dt, and plus the dbt term is sigma fx dbt. Sigma fx dbt. Okay. So what should I do now? I will take the expectation on both sides. And expectation is too simple. I can do this. So what am I doing now? I'm just taking this whole thing and copying it, pasting it here, and applying the expectation. Maybe I should use different color. So expectation on the left-hand side and expectation on the right-hand side. But you know very well, if I have expectation on the right-hand side, I can split the expectation on both of these terms separately to the term of dt and to the term of dbt. So expectation of dt term and expectation of this dbt term. But you know very well, the expectation of Brownian motion are simply the expectation of an integral or a Wiener integral. Like, I'm not going in these all the details, but the expectation of this term is going to be 0. If you compute the expectation of the term involving dbt is always 0. And there might be like, I should give a mathematical reasoning behind this, but I'm okay with this one for now because I'm not trying to make it more rigor. Then I have something left now. What am I doing is something like I'm going to switch some of the things. Like what am I doing is I'm writing this one E of df, and this one is like I'm taking this dt out. Like I'm interchanging this dt with the expectation that I can do if the function satisfies certain properties, like mu fx plus 1/2 sigma square fxx dt. Now I'm taking this dt on the left hand side. So I can write the left hand side is like I'll take this d out as well. So this will be d of dt of expectation of f is expectation of mu fx plus 1/2 sigma square fxx. Okay. Now what I will simply compute these expectations. And computing the expectation is just take the integral, multiply with the underlying probability, and we are taking the underlying probability to be p of xt. You know very well that thing. So since we want this Fokker-Planck equation, we have to drive something in terms of p only, not in terms of f, because we want this f to be totally cancelled from these all the terms. Okay, so this would be simply d of integral from negative infinity to infinity f, which is simply a function of x, p of xt dx, because expectation is whatever the function is multiplied by the probability and you integrate. Similarly, this is negative infinity to infinity mu fx plus 1/2 sigma square fxx multiplied by pxt dx. And like I will expand the right hand side to be two terms, mu fx pxt dx. Like I'm going to multiply this one with the first term and with the second term, plus 1/2 negative infinity to infinity sigma square fxx pxt dx. Now what I will do, I want like this fx to be converted into f only with no derivatives, and I want this fxx to be converted into f with no derivatives. And obviously, to solve these all the things, I will apply what we call integration by parts, and that's like something that comes from very basic mathematics. So I'm calling this thing up to here to be 1, and this thing up to here to be 2. So these are just names that I'm going to give to these things. So my first one is equal to negative infinity to infinity. I'm writing p first, and then I'm writing mu f x tx. Is that so? Okay, what am I doing? I'm writing mu with p. So I'm writing mu with p fx dx. So you know very well the integration by parts formula is integral u dv is uv minus integral v du. So I'm taking this thing to be u and this thing to be dv. So you know very well if my dv is fx dx, then my v is going to be equal to f. And I will put these values over here in this formula. Like I will apply this formula. This is my u, which is this one. This is my dv, which is this one. I will write uv. So this one would be equal to, my u is mu p of xt times f. And always the limit is from negative infinity to infinity minus integral v, which is f. And du is the derivative of mu times p of xt dx. So this is only I'm applying the integration by parts, and you know very well, like now I will only apply one assumption that this f is has a compact support. It means if you take f to infinity or minus infinity, this becomes 0. So if you apply this infinity limit here, this term becomes 0. And if you apply minus infinity here, this term becomes 0. This is my assumption. And like there are many reasonings behind these things. So I'm going to say, okay, this is 0. So then I have negative integral f partial by partial x mu p of xt dx. Okay, so this is the first term. Similarly, I can compute what is my second term. My second term is negative infinity to infinity. I think it's sigma. I will write sigma square p of xt and f xx dx, and I will do the same thing. I will consider this thing to be my u and this thing to be my dv, and I'll apply integration by parts, like it would be uv. So sigma square pxt, and if I compute v, that would be the first derivative of fx now, minus integral. So there's, I think, 1/2 here. So there would be 1/2 out. Yeah, negative infinity to infinity. Let me write here negative infinity to infinity as well. And now I have v, which is fx, and partial by partial x of sigma square pxt dx. And you know very well, like I will apply the same reasoning for this f of f, the derivative of f with respect to x to be 0 as well on infinity and negative infinity. Then my 2 would be equal to minus 1/2, because you can see I have this negative sign, I have this 1/2, and then I have negative infinity to infinity, and then I have f, what should I write? Okay, partial by partial x of sigma square p of xt fx dx. And since I told you like I want f only, not fx, so I will apply integration by parts again. And I'm not doing this thing. If you apply integration by parts, again, you will get this negative becomes positive, minus infinity to infinity. Now it becomes f only, and this becomes second derivative of sigma square p of xt dx. So this is my value of 2, and this is my value of 1. This one here, I will put these two values here in these, and then I'll compare the results. So put the values. So if I'm going to put these values, then obviously I'll be getting this thing, d by dt, negative infinity to infinity, f of x, p of xt, dt is minus negative infinity to infinity f partial by partial x mu p of xt dx plus 1/2 negative infinity to infinity f, the second derivative, sigma square p of xt dx. So the next thing that I'll do is, like, I will take this derivative inside, that will be partial derivative. I will take these two terms there, and since you can see f is here, f is here, f is here, dx is here, so sorry, I think this should be dx, and this should be dx2. So I will take everything on one side, take this f and dx common out of these all the things, take this derivative inside. So this will give me negative infinity to infinity. I'm taking f out of these all the things, so this This term, first term would be here, partial f by partial t, this one, partial p by partial t, because, I take this derivative inside, this becomes the partial derivative. This is called differentiation under the integral sign. And then you can see this is minus this term, that would be now plus partial by partial x, okay, mu p of x t. And now the final term is this becomes minus 1/2 times this term. So minus 1/2 partial 2 by partial x square sigma square p of x t. Then I have dx is equal to 0. So I have taken everything on one side. I have f multiplied to everything, and then integrated. So I can write these same things again. So I'm saying that this whole integral is 0 for any general f. So the mathematical property says that if this whole integral is 0 for any f, then the term which is multiplied with f should be 0 itself. And we can prove this thing as well, but this is all about mathematics. So we are not doing it. It implies I have partial p by partial t plus partial by partial x. And this is mu xt pxt, because I can write this explicitly pxt minus 1/2 the second derivative of sigma square of xt pxt equals 0. And this is what I call, you can see this is what I call the Fokker-Planck equation. And this is like what I have proved so far by using these only couple of pages. And you can compare this one with this one, like this is partial b by partial t, the derivative of mu with p. So the derivative of mu with p minus 1/2 second derivative of sigma square with p. And minus 1/2 second derivative of sigma square with p is equal to 0. So I started from an SDE, applied Ito's formula, and applied expectation, and then applied a couple of other properties like integration by parts or something else. And finally, I reached at something that I call Fokker-Planck equation, which is this one, So if you are given an SDE, as an example, as a simple example, if you are given an SDE, which is dxt, which is simple like dbt, so the Brownian motion. So if you want to derive the corresponding Fokker-Planck equation corresponding to Brownian motion only, then you have to consider this. If I'm going to compare this one with mu xt t dt plus sigma xt t dbt. So if you compare these two things, since there is no any dt term here, so I'm saying that my mu is 0. And since you can see that it's only dbt here, so my sigma should be equal to 1 here. 1 here, this is 0, so this is going to be dbt. So sigma is equal to 1. So if I put these two things in my Fokker-Planck equation, which is this one, so I'm putting mu 0 here, so this term vanishes. I'm putting sigma 1 here, so this is equal to 1. Then I will get something which is partial p by partial t. Okay, sorry for this, partial p by partial t minus 1/2 second derivative of minus 1/2 second derivative of sigma square is 1p. So the second derivative of p is equal to 0. So this is corresponding Fokker-Planck equation corresponding to Brownian motion. Okay, and like the process is Brownian motion, and this is the corresponding Fokker-Planck equation, which is I think what we call heat equation. Yeah, this is what we call heat equation. So you can compare an SDE with the Fokker-Planck equation easily. Okay, see you next time with something more interesting.